Methods of heat transfer. We can take heat and pass it along, or we can make things cold. Okay, so we're talking about methods of heat transfer here, hence the title. And we have three ways of actually conducting heat from one object to another. And I think I just gave one of them away. The first method we could use to actually conduct heat is simply called conduction. Surprise, surprise. And with conduction, what we pretty much have is objects touching. And I like to put objects touch in parentheses, because if you've seen some of my prior videos regarding electromagnetism and the fundamental forces, we know that objects don't actually touch, so to speak. There's a electromagnetic repulsion between electrons that kind of prevent this. But when objects touch, they can transmit energy from one to another. And we know this energy transfer, commonly is temperature for an average kinetic energy. But this objects touching transfers this amount of heat. And one of the things that really matters here, because when objects touch, one object's molecules are bouncing into the other ones, transferring that energy, transferring those velocities. That is that temperature. That's what we feel. But what really matters then is that you have a difference in temperatures. If everything is the same temperature, then touching two things together won't actually transfer any heat. If two objects are the same temperature, then they have the same average kinetic energy, which means that on average, you're not really transferring that energy or that velocity from one object to the next. The objects are just internally moving the exact same. So who cares? You don't have conduction. It's a difference in temperature that allows this to happen, because the fast-moving object, the high temperature, high average kinetic energy, can bump into the slow-moving object and speed it up. The equation we use to look at conduction is the following. An amount of heat transfer in an amount of time is equal to Ka multiplied by T1 minus T2, or T2 minus T1, depending on the direction of your transfer flow, divided by L. Now let's talk about what everything is in this equation. Q over here is the heat, or the heat energy. T is some amount of time. And this gets into a question that was asked in a prior video of how can we think about how long it takes for objects to heat up and cool down, because there's a time right there. Here, this A, we have as an area. L is some length, or a thickness, as some might call it. T's are just temperatures. That's the difference in temperatures we are looking for. And K is a little bit weird. K stands for a thermal conductivity. And honestly speaking, outside of the science worlds, you really won't see K being used at all. If you were trying to do something like insulate your home because you found that your attic is, or your upstairs might be very hot in the summer, very cold in the winter due to the attic. If you go into a Home Depot or a Lowe's or a hardware store and you start looking at insulation, you're not going to see K anywhere. What you're going to see instead is what is called an R value. R is a resistance, or a resistance to heat flow. Just like if we had a resistance of a resistor with electricity, that was how well some object is preventing the flow of current. R values are designated as 1 over K. So higher R values are better insulators. Lower K values are better insulators. And that makes sense because with K in the denominator, as K becomes smaller and smaller, R values increase. A nice way to think about this equation, if you ever absolutely forget it, is if you need to rederive it, think about a front door of a house. if you draw yourself a little door, there are a few things on this door that make sense in terms of heat transfer. Let's make the outside of this door over here very hot, like it's summertime, and the inside is very cold. We know that in theory, the energy flow should go from hot to cold through this object. Well, what would increase the rate of this heat transfer? This Q over T. Well, if you had a larger door or a larger opening, then there would be more opportunities for the hot object to transfer to the cold side. So a larger A will make that heat transfer faster. If you look at the length here, and this length is kind of like the thickness of the door, right here. If you have a thicker door, it's going to take a longer time for that heat energy from the outside to get to the inside, because that heat energy has to work all the way through every single particle to get through to the other side of the door. There's actually a really cool thing that occurs out in states like Arizona or the desert climates. They build solid concrete or stone walls on the sun-facing sides of the house, so that in the morning, that wall will heat up and it'll stay and become warm throughout the day. But the wall is so thick that that heat won't penetrate to the interior of the house until the sun goes down. Deserts have large fluctuations in temperature, very hot in the day but very cold at night. So during the day, the wall's thick enough so that the sun rays beating on that wall, which heat it up, they won't allow that temperature to propagate through the wall until nighttime, when they can warm up the house. So it's a very natural way of heating an object whenever you want it to be heated, just with this idea of a thermal energy transfer. And then naturally, the delta T, if the hot is even hotter, it's going to transfer faster than if those temperatures were closer together. Okay? So this is the idea of conduction. Now, conduction deals with objects physically touching, which I just mentioned a second ago that the sun is heating up the walls, but the walls aren't touching the sun. So what is happening there? This method of heat transfer or energy transfer is simply known as radiation. Now, a lot of people, when they hear radiation, they immediately start thinking about the world of nuclear, and they start thinking about like the dangers of it and whatnot. Really, nuclear power and things of that nature are actually very, very safe. But when we talk about radiation, we are just talking about an energy transfer due to light. That is actually what we're talking about, an electromagnetic radiation. And because this is just literally light, you don't actually need matter to transmit light waves. We know light as an electromagnetic wave, an EM wave, which means it can propagate through space, which is a vacuum. Now, this is a really nice thing because that means that the energy that these particles of light bring, and we can think about energy is equaling the HF, which maybe you've seen that before, maybe you haven't, or some people like to write it as H nu, where F is frequency, is H is Planck's constant. We'll come back to this idea later in this class when we get into nuclear. But we can bring in energy from something distant like a star and bring it into Earth and strike things. As a side tangent, whenever we actually look at things like stars, a lot of people like to say like, oh, that star is so bright, it must be so powerful. Brightness is not the best term to use when talking about the output of a star, or the energy output. Because if I take a flashlight 2 miles away, that flashlight isn't going to be very bright. But if you take a flashlight and you stick it right in front of your eyes, all of a sudden you're blind. Brightness is that measure of how something appears, but it is heavily affected by distance. What we use to measure energy outputs of things like stars is the luminosity. That references the actual energy output. And the luminosity of something like a star is equal to the following. It's equal to this value E, which is not the 2-point term from mathematics. This is actually an emissivity. It normally has values of 1, but technically it can range from 0 to 1. The emissivity goes down if there's like a dust cloud around you because it's harder for the light to get out. But normally we just assign it a value of 1 for most stars. And then there is a sigma value, which is known as the Stefan-Boltzmann constant. This is the Stefan-Boltzmann constant. Then we have the actual the actual area of the surface of the star itself, which for something like a sphere, if you're using a star, that's just going to be 4 pi r squared. And then the actual temperature of the star raised to the 4th power. Which is kind of a crazy power to raise things to, but that is how things go down here. And remember, this luminosity, this is an energy output for per time. It is similar to a Q value in some amount of time. Okay? It is just some energy per time. And the nice thing about this is this luminosity is not affected by distance because the star has these physical properties. The star has an area, the star has a temperature. Most of the time it's not covered with a dust cloud, and there's a constant there. So if a star is very close or star is very far, does not matter. The luminosity is the luminosity. Okay? So this idea of radiation or light is another way that we can bring in energy other than just conduction by having things touch. The last method, and this one is kind of similar to conduction, is what is known as convection. Now, if you have a home with central heating and air, or maybe you have a convection oven, then you might have some idea of what convection is, because fans tend to need to spin to kind of push air along, or you're just trying to get a bulk flow of matter. And that's really what convection is. It is a bulk flow of matter. We have convection for ovens, for AC units, for heaters, but there's also convection in like the Earth's mantle, right? There's a convection layer zone where bulk quantities of molten rock are being brought up to the surface, cooling off, and then sinking back down. And traditionally, when we think about convection, what we're thinking about here is if you have a hot set of material, hot sets of material rise, they displace material up top, which is traditionally cooler because as this hot material is rising, it is cooling off. As it displaces the cold material falls back down. And normally, if this is something like a pot of water on the stove, it heats up through to some source, becomes the hot material again, and begins to cycle. This is convection, okay? And we use convection not only for seeing it in boiling water for these kind of swirling effects, but like I said, in your houses, if you got central heating and air, this same idea will happen here. In our homes, what we tend to do is you'll have some register vents on your walls or in your floor. So this is like a large room. We'll tend to put register vents in these rooms. And then we'll actually have return vents. And these return vents have two purposes. One is so that as the air kind of comes into this room, it can convect out as we go through. And because this air is already slightly heated, your AC units have to do less work. We also use the same idea with ceiling fans, especially in the winter. If you have a ceiling fan, this is a poorly drawn fan, in the wintertime, you actually don't blow air down with your ceiling fans. You toggle a little switch and you pull air up. The idea is that when you pull air up, this air is going to go up here, and then it's going to fall down back along the walls. And in doing so, we are cycling air throughout the room so that wherever your heater is, in just one tiny spot in the corner of a room, you won't have a hot and cold spot in the room, but instead, the entire room will stay at one nice ambient temperature. So traditionally in the summertime, you run your fan so that the air pushes down and it's fast, so that you get more air past you. It allows you to evaporate sweat and water from your body so you feel cooler. But in the wintertime, we put our fans on a slow setting. We have them pull air up, and it more evenly warms our homes so that our rooms are more comfortable. So just a little fascinating thing about room design there. But these are 3 different methods we use for transferring heat energy. Conduction, objects touching; radiation, just light; and then convection, which is just a bulk flow of matter from one position to the next as it heats or cools throughout the system. So with these 3 methods, they're very, very helpful for what we're going to be talking about within this world of heat transfers and thermodynamics. Hope that worked out well for you. This right now is finished. We're going to come back to these ideas whenever we start looking at some examples and some intergalactics. But until next time, adios, and take it easy.